Hi there, welcome to your lesson on trigonometric identities. Before we begin this topic, let's do a little flashback to see the journey we've taken through trigonometry so far. We began with the unit circle. We noticed that the x value of a coordinate is cosine and the y value is sine. Then looking at that and saying opposite over adjacent is tangent, we can say then tangent is sine over cosine. We also looked at Pythagorean theorem for that triangle there. And remember, the unit circle has a radius of 1, so the Pythagorean theorem looks like this. But again, we just said that x is actually cosine and y is actually sine, so we can rewrite the Pythagorean theorem using sine and cosine. And that leads us to what is called the Pythagorean identity. These are some key ideas we've looked at so far. From there, we looked at special right triangles, triangles that have angles 45, 45, 90 or 30, 60, 90, and we noticed that the sides have a certain ratio or certain lengths. We then took those side lengths and put them on a unit circle. So in this circle, we took all those key angles, 30, 45, 60, 90, and all the variations of those angles, and therefore we could label each point on the unit circle, because when we know the angles and we use the special right triangles, we can find those exact locations. Of course, there's infinite angles you can have a unit circle, but these are the angles that often come up, so that's why we concentrate on these. After we had our unit circle with points, we know that each point here, for example, each x-coordinate is cosine and each y-coordinate is sine. So taking all the y values, for example, we can then graph it. So we take all the angles and we start graphing points. We know when the angle is 0, the y value is 0. We know when the angle is 15 degrees, the y value is that. We know when the angle is 30 degrees, we have that. And we put all the points together and we were able to create a curve for the sine curve. It's called a sine wave. So by graphing all the y values along a unit circle, we can create this curve and it goes forever. We also did the same thing for cosine. It also graphs as a wave or a curve of that type. However, cosine begins at 1, because when we have an angle of 0, our x value is 1 on the unit circle, and so on and so on. So that's the journey we've taken so far. We've arrived at the place where we can now talk about trigonometric identities. So these, sometimes if you research this on your own, you'll be a little bit, maybe you'll have a little fear in you, because if you look at what trigonometric identities are, you'll find all kinds of stuff. But let's begin here. What is an identity in mathematics? Here's an example of an equation. Let's say we solve this equation. Simplifying it, 3x equals 5, x equals 5/3. So taking that equation, solving it, we get this answer. That means this equation is only true when x is 5/3. That means if you substitute 5/3 on both sides, it will be equal. If you substitute any other value for x, it won't work. So that means this only works in this specific case. But let's look at a different one. Let's say we had this equation. You can pause and take a moment, try to solve this, see what happens. Well, what happens is when you expand this side here and combine things, you end up with two things that are the same on both sides. So the x's actually cancel and you're left with 1 equals 1. So what does that mean? There's no answer for x. Well, what that means is it doesn't matter what x is. X can be any number, because when you look at this stage here, you can substitute any value for x here and any value here, and it will always be true. So that is what it's called an identity. Here, it's an equation. There's only one value that makes it work. Here, any value of x works, so therefore it means that this equals this always. It's an identity. And to show an identity, we often use this symbol here. That means that this side and this side are identical to each other always. Okay, another way to say it is that this can be written as this. Another way of writing this is this. So it's always true. That's an identity. In trigonometry, we have some identities, but before that, let's look at these. These are examples of identities, right? This is the same as this. This is the same as this. These are all identities. They will always be true. Here's some identities we've seen in algebra. We know when we factor something like this, or sorry, when we expand this, we get this. So those two things are equal to each other no matter what a and b are. And here's some other rules like that. Those are all identities. In trigonometry, there's many identities. This is some of them. This is some more of them. So you're already getting a little fear now. What about, do I really have to know all these identities? No. If you're doing a very deep course in trigonometry, yes, you would. But we're doing just a broad, quick look at trigonometry. So the only ones you need to know from all those I just showed you are this one, which we've already studied, Pythagorean identity, and also this one called a double identity, and here's another double angle identity. So these are the ones we're going to focus on. Some other things here you've seen already are this. This is a rule about angles that lead to the same sine value and cosine value. But we haven't memorized that as a rule, but we've used it in the work we've done. And also, you've seen all this. These are just our law of sines, law of cosines, area of a triangle. These formulas we know. But today, when we focus on identities, we're going to look at these ones in green. Okay, so let's recap. The identities you should know are these. The Pythagorean identity looks like this. The idea that tangent of an angle is sine over cosine. And the double angle identities are the new ones we're going to look at. And they are this, this, and this. So cosine of 2 theta equals all three of these. They all work for that. And sine of 2 theta equals this. Take a moment now and write these identities down. 1, 2, 3, 4, 5, 6, all 6. Okay, if you don't need to know this, but if you want to know this, I'm showing you in the next 3 slides the proofs for where these identities come from. Because maybe you're wondering, where do these come from? How can we prove these work? Well, these are the proofs here. So pause after I show this, pause and study it if you want, but you don't need to know this, so don't worry if you don't want to. So here is the double identity for cosine, double angle identity for cosine, which when it equals that. Here's the proof for that. Pause if you want. Okay, next, the double angle identity for both of these ones, cosine 2 theta also equals these two things. Here is the proof for that. Pause now if you need to, or if you want to. And finally, the double angle identity for sine, which looks like this. Here's the proof for that one. Pause now if you want to read that. Okay, but we're less concerned about proving them and more about using them. So let's take a look. Here we are given that sine of x equals 3 over 4. Okay, find cosine. Well, we know that the relationship between sine and cosine can be shown using the trigonometric identity. So we're going to write the Pythagorean identity. So we write that here. We substitute our 3/4 for sine, and basically we just solve this equation. We've done this already, so this should look familiar. Solving that, we get a cosine value of √7 over 4. Now, here it says, find the exact value of sine of 2x. Well, we have our double angle identity for sine, so we know that equals this. And we already know sine, and we already know cosine because we just found it. So it's just a matter of plugging values in now. So you plug in the 2 values you know for sine and cosine, and you get that value there. Pause if you need to kind of take a look a little bit more and take some notes. Okay, let's look at 2 more simple ones like that. Now we're looking at cosine of 2 of x. So that one we know has 3 different ways you can write it. So you can choose any of the 3 ways. I chose this way here. And using our double angle identity, now we can expand it, putting in what we know. We know sine is 3 over 4, so I'm just substituting into this formula the sine value, and I get this answer. That simplifies to this. Okay. In D, now we're looking for tangent of 2x. So now you look at, whenever you see tangent, you should think about the property where we know tangent is actually sine over cosine. And since we have 2x here, we're going to write 2x and 2x here. So now you simply put in your values for sine 2x and cos 2x, which we found. For example, here's cosine 2x, and in the previous slide we had sine of 2x. And those are our values there. Simplify that, and we get this answer here. So these are pretty simple. This first question is pretty simple. It just shows you how we basically use the rules as formulas, right? We start with a sine value, and then we use these formulas that we've been presented with. So now try the same thing with this one here. You're given this sine value. See if you can find these 4. And let's check our work. Here's A and B. Pause if you need to kind of check your work closer. And here's C and D. Great, let's move on. Here's another equation we have. We have 2 times cosine of 2x equals 1. Let's solve it. So I notice here that this is 2x and this is x. We've looked at one like this before. So we're going to do some different things here. So I'm going to pause now, and you're going to come back in video number 2, because I notice I'm already at the 10-minute mark almost. I know I need a couple more minutes to explain the next few slides. So pause now. There will be a second video that continues from this point forward. So you have now a basic understanding of the 4 or 5 main trig identities we need to know. And now we're going to look at using them in tougher problems. So see you soon in the next video.